The effect of training duration on anaerobic contribution in distance runners. A presentation by Andrew Kidcalf. Athletes are highly trained individuals varying across all aspects of sport. Distance runners in particular all have a high aerobic capacity and depend on physiological parameters such as maximum oxygen uptake, or VO2 max, to maximize performance. For this reason, anaerobic capacity may play an important role in endurance events that commonly require 90 to 100% VO2 max. Anaerobic characteristics have a positive influence on performance and may determine the runner's ability to produce energy during or near the end of the event. A study revealed that endurance athletes had lower levels of power output and fatigue in comparison to team sport players. A possible reason may be that the majority of field sports require relatively short, high-intensity bursts of exercise rather than continuous, moderate-intensity exercise. Currently, there is little evidence regarding distance runners and anaerobic capacity, which suggests that it does not play an important role in performance. To confirm, a study revealed that approximately 75% of an endurance athlete's training schedule is low intensity. Energy contributions can be determined for athletes through testing measures. This can be helpful for monitoring training and performance progress. When testing for aerobic capacity, VO2 max is a widely used measure for determining functional capacity of the cardiovascular system. When testing for anaerobic capacity, maximally accumulated oxygen deficit, or MAOD, is the most accurate method used currently and also the most widely used approach to date. MAOD can be useful for establishing sport-specific training schedules at high intensities. With regards, the purpose of this study was to establish the anaerobic capacity of distance runners, determining whether varying durations of training per week affect the contribution. Participants completed 3 separate test protocols on cycloergometers, which included warm-ups and rest periods. Figure 1 provides the order of the testing procedure. Protocols 1 and 2 were incremental tests to establish VO2 max and to predict a supramaximal workload for Protocol 3, the MAOD test. 15 college students participated in the study. They were separated into 3 groups that were determined by the amount of training per week that each person partakes. They included less than 180 minutes, 180 to 250 minutes, and greater than 250 minutes a week. The VO2 max test and the submax test both contained 5 stages of submaximal exercise at varying durations, with increasing intensities per stage. The supramax test was set at 120% of the participants' VO2 max, which was determined by a linear regression equation established from protocols 1 and 2. Data was collected during each test using gas analyzers, which collected VO2, VCO2, and RER. 3 single-factor ANOVAs were run on Windows XL, testing groups for VO2 max, MAOD, and anaerobic contribution. Figure 2 displays all the participants' time to exhaustion for Protocol 3, the MAOD test, with participants on the x-axis and time presented in minutes on the y-axis. As you can see, there is no obvious correlation between any particular participant, questioning the predicted workloads that were set. Table 1 displays the group means as well as a total for all participants for VO2 max, MAOD, set workload for the 120% VO2 max, and anaerobic contribution. You will notice that each result is similar in number, despite each group being distinctly separated by weekly training durations. The means and standard deviations per group for each variable remain reasonably alike throughout test protocols. The purpose of the study was to determine the anaerobic capacities of a group of distance runners. It found no significant difference between each group for each protocol, and as a result, the null hypothesis was accepted. Participant differences may have contributed to the results, such as gender, age, and training intensities. The study supports current literature stating that VO2 max is a significant predictor of running performance in relatively matched participants. In addition, these results support the validity of the MAOD test in predicting supramaximal intensities. With similar anaerobic contribution among participants regardless of weekly training duration, suggests that other physiological factors are involved. One possible factor may be the types of muscle fibers of each participant. Endurance athletes' muscles are mostly made up of slow-twitch muscle fibers, which are highly oxidative and resistant to fatigue, as opposed to fast-twitch muscle fibers, which are low in both oxidative enzymes and fatigue resistance, and are useful for explosive, short-duration exercises. An individual's VO2 max is specific to the exercise mode in place. This reveals a limitation to the study in that all participants were tested on cycle ergometers rather than treadmills. However, a study suggests that muscles adapt specifically to a given exercise over a period of time, known as familiarization. To ensure this occurred, participants were encouraged to warm up on cycle ergometers prior to test protocols. A focus for further study should be on the group of participants, standardizing each group to a specific intensity of training, for example, 50 to 90% of VO2 max, and include a record of training history as an indicator of individual skill levels. In summary, this study has established the aerobic and anaerobic capacities of a group of distance runners, each varying in duration of training per week. Similar results for both aerobic and anaerobic capacities among the participants suggest that training duration has little effect on the energy contribution throughout a high-intensity performance to exhaustion. Anaerobic factors may be beneficial to endurance runners in terms of the power output required at crucial stages of a race performance. In order to improve one's anaerobic contribution, a training schedule should be in place that incorporates a range of exercise intensities, ensuring that the muscle's ability to produce energy varies from both aerobic and anaerobic systems.